This video marks the beginning of our next unit of study, and it's a smaller unit on field forces. And this particular video will focus on the concept of gravity. Just two learning targets that we have for this particular lesson. The first of which, I want us to be able to describe the nature of field forces and compare them to contact forces. Now before you go on, pause the video and just take yourself a few moments to think about what do you think a field force is, what do you think a contact force is, and jot your ideas down. So you've had a chance to jot some initial ideas down about field forces and contact forces. Let's examine what these are. So a field force. Field forces do not require contact between objects to exert a force. In other words, what we're saying is they can act over a distance, that the objects can be separated by maybe a few inches, maybe miles, even hundreds of millions of billions of trillions of kilometers, perhaps even. One example of this, and it's the most common example, the one we are most familiar with, is gravity. Gravity is absolutely a field force. For example, the moon is held in orbit. It goes around the Earth and it's held in that orbit due to the force of gravity. Now obviously the Earth and the moon are not in contact with each other. Okay, they're not touching each other, yet there is still a force pulling the moon towards the Earth, and actually there's also a force pulling the Earth towards the moon as well. We know Newton's third law says that if the moon pulls the Earth, then the Earth has to pull the moon, vice versa. Okay, and obviously they're not touching each other. That makes it a field force. You might have a hard time visualizing what a field force would look like, or how we'd even describe it. Well, one way that scientists go about visualizing field forces is that they'll be represented by field force lines, or just field lines. So for example, if we have two objects here, where say for example the blue dot here might be the Earth, and notice it's a little larger, and the yellow dot here, or orange, whatever color you want to call that, that's the moon. And then you'll see these arrows that are all pointed towards these two objects. The arrows pointed towards the blue dot for the Earth, the orange dot for the moon. That represents the gravitational force that would pull objects towards those celestial beings. Celestial beings being things in the sky, the Earth being in the sky, and the moon being in the sky, etc. And so we can see that if there's an object that's traveling anywhere towards the moon, maybe say in this direction like so, it'll get caught up in that field force and it'll get pulled towards the moon perhaps. Or maybe if it's going this direction like before, but maybe it's going a lot faster, it might be able to go around the moon, but then it'll get pulled in towards the Earth by its field force. So sometimes these field lines are used to help us visualize these field forces because they do act over distances, so we aren't able to necessarily see them. Another thing about field forces is that these force fields, they get weaker as you get farther from the object exerting the force. So I have a visual depiction here to help you understand this idea. Let's say this is the Earth, and then like we showed on the previous slide, we can draw arrows that represent this field force of gravity pulling objects towards the Earth. Well, if we just draw, say, 4 lines, it doesn't get real easy to understand this idea of why this force would get weaker as you get farther away from the Earth. But let's say I put in a whole bunch of field lines, something like this, where I can see all these field lines attracting objects to the Earth. Notice if I'm really close to Earth's surface, these field lines are incredibly close together. They're very dense. But if I'm far away from the Earth, let's say I had an object way out here, and if you visualize these lines extending from the Earth, notice they're spreading out. Okay, these lines get farther and farther apart if you just visualize them extending in a straight line. So if we had an object that's way out here, maybe millions of miles away from the Earth perhaps, there would not be nearly as many field lines close to it. And so any field force, whether we're talking about gravity or later on we'll talk about magnetic field forces and electric field forces, they always get weaker as you get farther from the object. And we can visualize that with these field lines like so. And here's just a note here about what I've just said here. Note the gravitational field lines are more dense closer to the Earth. This is because the field forces are stronger closer to the object that exerts the force. Unlike field forces, contact forces require objects to touch to apply a force. These contact forces, these are the forces that you probably usually think of whenever you think of applying a force to something. So for example, let's say we had a box sitting here on the ground or a table. It really doesn't matter what it's on, okay? And let's say you're going to push the box, okay? You want to apply a force to it. I want you to pause the video and ask yourself, what do you have to do in order for you yourself to apply a force to that box? So you've had a chance to think about this, and one of the things that probably crossed your mind is you actually have to touch the box. There is no way that you can be Yoda from Star Wars and play with the, quote, force, so to speak. You can't just stick your hand out 5 feet away from the box and lift it up. That's impossible. So if you stick your finger out and notice the separation here between the finger and the box, there's no way you're going to be able to apply a force to the box because you're not touching it. However, if you do touch it, if you do touch the box, now you can push it. So if we have no contact, there's no force between the hand or the box. If I do touch it, if there is contact, we can apply a force. That would be the same thinking as, say, if I want to tie a rope to the box to lift it. If that rope's going to apply a force to the box, say this rope up here is attached to something, maybe a pulley or something on the ceiling. If I don't actually tie the rope to the box, if it doesn't touch the box, there's no way it can apply a force to it. So obviously I want to tie the rope to the box, something like we're seeing here, and now the rope could actually apply a force to that box. So field forces are very different than the forces that we experience a lot of times in our everyday life, just because they don't have to touch each other. The field forces of the objects don't have to touch each other. That being said, as we've already talked about, gravity is a field force for which we are very familiar with because we're kind of stuck to the Earth because of it. Alright, just a couple of review questions here about what we've learned so far. So first of all, the question is, what is a field force? So please pause the video and try to answer this yourself. Write it down in your notes, whatever you want to do. Ready, set, go. So you've had a chance to think about this question and jot down your thoughts. Here's my answer to this question. I write, field forces are forces that can act over a distance between objects. They do not require contact between the objects for a force to be exerted. Next question. How does the distance away from an object affect the size of the field force it can apply? Again, pause the video. Please answer this yourself. My answer to the question, the force field for any field force gets weaker as the distance away from the object increases. Thus, field forces get weaker with distance. Farther away from the object, field force strength goes down. Pretty straightforward. Alright, we have looked at the first learning target here. We have described the nature of field forces, and we have also compared them to contact forces. Alright, second learning target here is more specific. We'll only be talking about gravity. We're asked here to identify and explain the factors that affect the gravitational force acting between objects. Before we go to the next slide, please pause the video, and if you would, go ahead and see if you can jot down some ideas about what factors do you think that will affect this gravitational force. In other words, what we're saying is, what things would change about objects that would cause a change in the gravitational forces that attract them. So you've had a chance to think about this a little bit. Let's go ahead and see what the notes have to say. So capital letter B here is gravity. What this brings up here is Newton's law of universal gravitation. Not only did Newton have his 3 laws of motion, with which we're very familiar with, he also had this law of universal gravitation. And according to this law of universal gravitation, it says, all objects in the universe attract all other objects in the universe by the attractive force of gravity. Notice here the phrase, all objects attract all other objects. So it doesn't matter what the object is, doesn't matter what object we're comparing it to. If the two are in this universe, They are attracting each other by the force of gravity. And do notice it is an attractive force. Gravitational forces are always attractive. They pull objects, or the forces are directed towards each other. They're never repulsive. Gravitational forces are never repulsive, pushing objects apart. That never happens. Now, another way to think about this, and there's a legend, a story dealing with Newton, of him sitting under an apple tree and an apple falling from the tree and hitting him in the head, and then all of a sudden this idea of gravity dawned upon him. That in all likelihood did not happen. In fact, probably something not even close to that happened. But to put it in perspective, a phrase that's often used, or an idea that's often used, is what Newton realized is that this same force, this gravity force, it's the same force that keeps the moon in orbit around the sun, that makes an apple fall from a tree. So Newton's thinking about what this force is that causes the moon to go around the sun, and the moon to go around the earth, not to orbit the sun. And I notice my notes here are backwards. Obviously the moon does orbit the earth. So for the moon to orbit the earth, or for an apple to fall from a tree, Newton recognizes that it's all the same force. It's gravity. And he says that every object in the whole universe attracts every other object. That's pretty daunting. All objects attract all other objects. How in the heck could that happen? How could every single object attract every other object in the universe? And why don't we see that? Because obviously we're kind of stuck here on Earth. Why don't we experience this attraction between everything in the universe? Well, there's a very good reason for it. That reason deals with the two factors that affect the gravitation force acting between objects. These two factors that affect this gravitation force are the mass of the objects that we're considering and the distance between the objects. So the mass of the objects and the distance between them. I want you to consider a problem here. So now we're going to talk about this mass idea. My question is this: which pair of planets do you think has the greater gravitation force pulling them together? And here are your two options. Here we have these two planets. Notice we have one kind of shaded in a purplish blue, and this is more of a pinkish purple color. And then I have another option. I have this pair of planets. And notice that they are much smaller, so I suppose that means we assume that they are less massive. And also notice that they are the same distance apart. Okay, these two sets of planets are the same distance apart. And you might say, but wait, these bigger planets look like they're closer together. As far as just the distance from the surfaces of them, you would be correct. But when we talk about distance, what we're talking about is the distance from the center of mass. So notice the centers of the planets are lined up. So these two sets of planets are the same distance apart. So pause the video and ask yourself, which one do you think has the greater force of attraction of gravity pulling them together? I think intuitively, most of you will probably say, well, it's this first pair. These larger planets should have a greater gravitational pull or greater gravity force pulling them together. And your instincts would be correct. Okay? And that's because the greater the mass of the objects, the more gravitational pull they exert on one another. In other words, we're saying pair 1 here, the top pair, that would have the greater gravitational force pulling each other because they're more massive. Alright, second thing I want you to consider. Now we're going to be talking about that distance portion. We said the gravitational force was affected by two factors, one of them being mass, the second one being distance. And I'm going to ask you the same question. Which pair of planets do you think has the greater gravitational force pulling them together? This time your options are a little different. Okay, in our first pair we have two relatively small planets, and you can see how far they are apart. And then the second pair, we have two equally sized planets as we did in the first pair. So we'd say that they're the same mass as these two are up here. But notice they are much closer together now. So again, pause the video and ask yourself, which pair do you think will have the greater gravitational force pulling them together? I think our instincts probably lead us to say it's the second pair, these two that are closer together. And if that is in fact what your instincts tell you, you would be correct. Because the closer objects are to each other, the greater the gravitational pull they exert on one another. So in other words, here it is pair 2 that has the greater gravitational pull. Once again, I have several review questions for you to answer. And again, for each of these, once the question is presented, please pause the video, answer it yourself, perhaps write down your answer before you play the video again, and then see how well it agrees with how I have answered the question. Alright, first review question. True or false? You are being attracted to a pebble on the moon right now as you watch this video. This statement is in fact true. According to Newton's law of universal gravitation, all objects, that would include you, you're an object, they attract all other objects in the universe. This pebble that's on the moon's surface is also in this universe. And we're attracted by the force of gravity. So yes, you are currently being pulled, if only slightly, toward the moon by a lunar pebble. Pretty crazy to think, but according to Newton's law of universal gravitation, that is absolutely the case. Next question. What two factors affect the amount of gravitational force or gravity attracting two objects? Explain how each affects this force. The two factors that affect the gravitation force between two objects is the mass of the two objects and the distance between them. And as we saw in the previous examples, the gravitational force increases as the mass of the object or objects increase and as the objects get closer together. Now, one point I'd like to make here that I did not really make earlier in the examples that I was giving you is notice here I say the gravitational force increases as the mass of the object or objects increase. It's not just the mass, it doesn't have to be the mass of both of them. If I have two objects and then one of them suddenly gets larger, has a larger mass, even though the other one might remain the same, that will increase the gravitational force acting between them. It doesn't have to be both of them, only one mass has to get bigger. And also keep in mind Newton's third law. When we talk about the mass of one object getting bigger, that increases the gravitational force that's attracting both of them to each other. It's not just one of the forces increases. Because recall, according to Newton's third law, whatever force, say for example, the Earth pulls the moon with gravity, the moon pulls the Earth with the exact same force back. That's Newton's third law. Alright. Next review question. If you drop the pencil you are holding in your hand right now, why does it fall to the ground or maybe the table instead of being pulled to your chest? Because after all, you are being attracted to the force to your pencil, and the pencil is also being attracted to you by the force of gravity. So why do you think that is? Hopefully, in your thinking here, you were thinking about those two factors that affect the force of gravity between two objects, and in this case the important factor is the mass. So while Newton's law of universal gravitation does explain that you are applying a force of gravity to your pencil and also it to you, you are not nearly massive enough to overcome the Earth's gravitational pull. Obviously the Earth is far more massive than you. It has way more mass than you do. And so its gravitational pull on the pencil is much larger than your gravitational pull on the pencil. So that's why if you drop the pencil, it falls to the ground or to the table or whatever it happens to land on instead of flying to your chest. Alright, last review question. Suppose you are going skydiving. So you're way up in the air, maybe 30,000 feet up in the air, for example. When you jump out of the plane, why are you pulled to the Earth instead of to the sun? And the reason I ask this question is, after all, the sun is way more massive than the Earth. Now, if you didn't know this, I have some numbers here for you. You don't need to remember these numbers. These are just to put this in perspective. The mass of the sun is 2 times 10 to the 30th kilograms. So if you're not real familiar with scientific notation, this would be 2 followed by 30 zeros after it, kilograms. Where the mass of the Earth is only, 6 times 10 to the 24th kilograms. So that'd be 6 followed by 24 zeros after it. In other words, what we're saying here is the sun is about 1,000,000 times more massive than the Earth, roughly. Okay, 1,000,000 times more massive. So it'd take 1,000,000 Earths to equal the mass of one sun. So why do you get pulled towards the Earth even though it's way less massive than the sun? Go ahead and pause the video, think about it. Now, considering our last example, you might be wondering why this is. After all, in the last example, we said the pencil gets pulled to the Earth instead of to you because the Earth is way more massive than you are. Well, if I use the same reasoning here, we might say, well, it's the same thing. The sun is way more massive, and when I jump out of the plane, I actually get pulled towards the sun. But consider this. You're a really long ways from the sun. Okay? While the sun is much more massive than the Earth, you are also much closer to the Earth than to the sun. And recall, if I get the farther I get away from an object, the less the gravitational pull. So because that sun is so far away, its gravitational pull on you is not even anywhere close to the gravitational pull from the Earth. Even though the Earth is way less massive than the sun, you're obviously much, much closer to the Earth than to the sun. The sun's approximately 93 million miles away. So that's a long ways away. So the gravitational pull acting on you from the sun would be incredibly small compared to that of the Earth. Alright, this concludes our lesson here on field forces and specifically on gravity. You can see we have described the nature of field forces and compared them to contact forces. And then in the second part of the lesson, we identified and explained the factors that affect the gravitational force acting between objects. In the next lesson, we'll be looking at how we actually go about using Newton's law of universal gravitation to calculate the amount of gravitational force acting between two objects.